Hello, everyone. This is Amir from Audio Science Review. We're going back to school again and covering the topic of jitter. It's a common technical buzzword that people throw around, whether it's people selling you cables or tweaks for your audio, or people talk about measurements and what have you. So I thought I'd dig in and actually tell you what it really is, what it's not, how we measure it, what are the audibility aspects of it, because there's just tremendous amount of confusion on what it is. The concept applies to digital to analog converters, a DAC. If you look at this simplified picture I have here in one of my older articles, you need a few ingredients to produce the output of a digital to analog converter. It needs the audio samples, obviously, those are just digital values, and tells the DAC, produce this value, then produce this value, then produce this value. The DAC is running at certain sample rates, so if it's running 44.1 kilohertz, ostensibly you need to have 44,100 samples a second. So there's a thing called the clock, which pulses and says go, and output comes out, and then it ticks to the next one, and another output comes out, and ticks and ticks and ticks, and the analog comes out. What the DAC does is that it also has what is called reference voltage, which I won't talk about much today, but it can look like jitter contribution. In that it takes this reference voltage, let's say it's 3 volts, and then it divides it by the steps that you tell it. So this sets the sort of maximum value, and then when you give it a digital sample, you're saying, give me a ratio relative to that. This needs to be quite accurate, obviously, this reference voltage. If it's not accurate, then you're obviously going to produce garbage. And turns out this is hooked up to a power supply that's also being driven by the rest of the system, and noise gets in there. It can also impact the analog output of the DAC. Likewise, if clock pulses, their timing vary. If they're run slow or fast, it's all right. Our ear's not very sensitive to that if it runs even 1% too slow or too fast. But if it moves back and forth, it modulates these samples and produces an analog output that just got distortion in it. This is not a good picture. I'll show you actual demonstration with Audio Precision Analyzer later on. So this is the concept that we're focusing on, which is clock pulses, and can they get jitter induced to them, and what that looks like, and what have you. Now, the father of digital audio, one of the most famous fellow by the name of Julian Dunn. He worked for Prism Sound and then later on Audio Precision. And he's responsible for a lot of specifications on digital audio. And I recommend that you go and download his papers. You have to pay, unfortunately. I don't think there are free copies of it out there. But Audio Engineering Society, you go there and just look for Julian Dunn and jitter and these titles. I'll put a link in the description for them. But he did a simple math. He took the mathematics of jitter, which is a sinusoidal, assuming you have a sine wave and you mess up its timing with another sine wave. Basically what happens is that the phase of that sine wave gets modulated yet again. This is a gnarly formula to try to resolve, and I'm not going to walk you through it, but you can read the math. But it's done some simplifications, and turns out you can predict the interference that you get from jitter, and it just becomes proportional to the frequency of your source signal. And turns out if you just have 500 picoseconds of jitter, it's enough to step on the lowest bit in a 16-bit sample. So what is a picosecond? Is 1 trillionth of a second. So very, very, very small number. So 1 nanosecond would be 1 billionth of a second. So half a billionth of a second is enough to disturb a 16-bit signal. And I'll show you again examples of this. So, and that's for 16-bit. For 24-bit signals, this number becomes ridiculously small, like 10 or 20 picoseconds. So as much as its timing value is small, the distortion that it generates is big. And if you can grok what this says, it basically says if you have a source signal and you modulate it very small amount by modulates timing, you wind up with two sidebands, one above and one below. And these are the distortion spikes that are unwanted and we don't want in our signal. So the harm with jitter isn't that the timing of a signal moves back and forth. You often see YouTubers or journalists show you a visual picture where they take a picture, like let's say my hand, and they blur it out multiple times and superimpose them and say, this is jitter. It is not. How are you going to see a timing difference of a billionth of a second? You're not right. That thing is not moving in time a billionth of a second, or to cause problems, or nobody would listen to LPs and tape decks and what have you. So it is not a timing problem. Our ear is not anywhere close to sensitive enough to hear this as a timing problem, but it can hear this as a distortion and an artifact. So Julian Dunn went on and came up with a clever test signal. The sine wave, it's not a good signal to use for testing in general, because it's a mathematical function that it has these fine gradations, and you can convert it to integer values, which is what the digital audio is. But he came up with a simple way to generate a very pure sine wave without it being a sine wave. And what it is actually a square wave. So, and it cycles between two hexadecimal numbers if you're computer science. If you're not, don't worry about it. So basically we have a square wave. The square wave for 48 kilohertz sampling, it's always 1/4 of the sampling rate. So 48 kilohertz, which is what I use for testing, 1/4 of it's 12 kilohertz. So we have a square wave running at 12 kilohertz. Remember what I said about square waves. If you chop off their spectrum above the main frequency, you actually get a sine wave. So indeed, if we have a 12 kilohertz square wave, but we chop off everything above 24 kilohertz, which is the bandwidth that we have in a 48 kilohertz sampling, everything gets thrown out and we wind up with a pure sine wave. And all we had to do digitally, if we look inside of the signal, which is called the J test or jitter test, all it has is a square wave in it. That goes from this to this. Now, he was clever in that he added one more thing to it. 250 times a second, he adds one bit to the number and he subtracts one bit to the number. So what happens is that this number goes from C000 to BFFFF. So just think of this as if I go 9999 and add one to it, it becomes 10,000. So all the digits have changed. If I take one away from 10,000, all of them becomes 999. The amplitude change is infinitesimally small, yet it generates a lot of activity. All the bits have to toggle. And when all those bits toggle, if there is jitter, we get to see it more often. So a common misconception about J-test is that it actually creates jitter. It by itself can't create jitter because it's just a file that you play. Literally. I'm not going inside this DAC and injecting jitter into his clock. I have no access to that. All I can do is feed it a signal. And we happen to pick a signal that is A, easy to create, and B, we're constantly toggling his bits without changing the form of that signal that ultimately is reproduced by the stack. So what does that look like if we just took a spectrum of J-test signal and band limited it, so we're not looking at the harmonics of square waves? So we see that pure 12 kilohertz tone that I talked about. So that's what this spike is. This is our wanted signal. Inside of it, as I mentioned, we're also 250 times a second. We have a square wave. What is the spectrum of a 250 hertz square wave? It's 250 hertz and then 3 times higher, 750, and then 5 times higher and so forth, and the amplitude goes down. Now, this is visible in here because the audio precision here is analyzing a digital signal, so it has no noise. So I'm able to go to minus 180 dB, very, very low noise floor to expose these. Even state-of-the-art DACs can't go this low. As a result, you usually don't see any of these. Maybe you see the first or second, but you don't see any of the other ones. So as a typical rule, when I run the jitter test, you want to see this and basically nothing else, because these other ones are all in the noise floor of the system. Anything else is unwanted. And if it's jitter, it will show up as symmetrical tones, which I'll show you in a second. Hopefully you're with me, but I think it's important to understand what a J-test signal is that we use for this test. Again, it has no jitter in it. A digital file sitting on disk is constant. It can't have variations, and it's not sitting there dancing around. It's just a set of numbers. We play those set of numbers, and it's two square waves nested in each other. They go in a DAC. What comes out of DAC is actually a sine wave because we don't let all the harmonics come out. And then we capture that analog waveform, and we apply spectrum analysis on it, and we see what that looks like. So let me switch to my audio precision analyzer and show you what's going on. So this is a, oops, let me get rid of this title here so you're not confused. So I've got an SPL Phonitor X. It's a $2,500 DAC and headphone amplifier. I just reviewed it tonight. Unfortunately, it has a very poor DAC section in it. Very disappointing is what you find in a $10 DAC. I don't know what's up. They claim to have a very good DAC implementation, but certainly wasn't the case here. So I couldn't get the USB port working, but Toslink optical works. So I hooked up Toslink, and I got this display. But notice what happens now. I've got a USB cable that's also connected to it. So I'm going to plug this in. I'm not going to use USB. So this is still configured to receive data over Toslink, and my audio precision analyzer is sending a Toslink data. So let's go ahead and run this USB. Notice what happens, how noisy it got. This is actually clean. When I ran it during the review, the spikes were just far, far worse than this. Maybe I can stop this running one more time, see if we get lucky. And it shows the much worse input. No, it's insisting on not doing that. But anyway, you can see that there's a lot more activity now here than there was. So mere fact of just hooking up a USB cable to the unit allowed some activity from my computer to bleed into there. And that leaked into the DAC and produced all these extra noise in here. Like you can see, there's more noise in the lower section of this display. So oftentimes when I run this display, it's not really a jitter test. It's actually just anything garbage. Our wanted signal, again, is this over here, the spike here. All this other stuff we don't want, and if they bleed into this, we don't like. So let me disconnect this and delete the USB one. So this audio precision analyzer is quite clever in that I can take any of the digital outputs, the Toslink and coax, for example, and I can tell it to wiggle their clock. So it can actually induce create a noisy interface, as if you had a really cheap source that didn't have a good clock accuracy. And I turn that on. I can tell it what I want that jiggling to look like, the jitter spectrum. For sake of simplicity, we're going to say sine wave. We're going to say 1 kilohertz. And I'm going to say add 4 nanoseconds to it. So 4 billionth of a second. And let's see what happens when we do that. Notice what's going on now. Look at these two pulses in here. The signal's at 12 kilohertz. We get one at 11, and we get one at 13 kilohertz. Why do we get one at 11 and 13? Because the sidebands that show up as jitter are the sum and difference of 12 kilohertz relative to our jitter frequency. So if our jitter frequency is 1 kilohertz, we get one at 12 minus 1 at 11, and 12 plus 1 at that. So if I then change this to 4 kilohertz, 4 kilohertz, you'll see that we should get one at 16 kilohertz now, and we get one at 8 kilohertz, right? So 4 plus our tone, 4 minus. So oftentimes when I run this, if I see something like this, I tell you there's a jitter frequency at 8 kilohertz and or 4 kilohertz, and this is how I know what the jitter frequency is, because I look at the difference between these and I can see it there. Now notice how tall these spikes are. I mean, if this were distortion, we're already up to minus 92 or so. I mean, minus 88 or so. even though we only added 4/billionth of a second worth of timing difference, 4/billionth of a second, really, really tiny amount, the distortion spikes are quite high. I mean, many DACs have harmonic distortions, so way below this. And here we're generating distortion products that are really tall. Worse yet, we're generating distortion products before our signal, in addition to after. The way psychoacoustics works is that there's a shadow that the signal generates, the stronger signal generates, that masks the audibility of things in front of it much more than masking things that are below it. So as a result, these tend to become more audible than the ones after. Harmonic distortion is always after, so they get masked more than equivalent jitter would. So jitter is not a good, signal, if you will, for to have in there as far as distortion. We want to have a lower threshold there. So we also have a choice of spectrum. So instead of a sine wave, I've changed it to square wave. And let me change this back to 1 kilohertz. And let's see what we get. Now, what happened when I instead of 1 kilohertz, when I had just a sine as the spectrum, I only got 2 spikes. But the moment I changed it to a square wave, why did I get all these other ones? Remember what I explained the square wave to be, right? It's 1 pulse plus harmonics forever. Each one of those sine waves in a square wave generates its own jitter. This is important because these devices are what we call mixed signal. They have a digital input that receives digital data, and some of them have microprocessors in them and so forth. And all of those digital circuits work on square waves. So if they're going to interfere with the rest of the circuits, oftentimes that interference in the form of a square wave. So you can easily see a train of these pulses in this jitter spectrum. And whenever I see that, I mention in my review that, hey, there seems to be a square wave interference, because I can recognize this kind of, pattern to it, as opposed to, just as pair that would be for sine wave. Now, I can also change this to be noise. Noise, it's also a common interference. A CPU that's running inside this device is doing so many random things that its activity may not be just a simple, here's a pulse. It's just many, many, many billions of operations a second is doing. Notice what happened when I changed this to noise. I no longer get the individual spikes. Why? Because noise has every frequency known to man. Therefore, it raises the noise floor of the system proportionally. So a jitter, when it has a spectrum of noise, that means it's randomly changing the clock, it basically just raises your noise floor by equivalent amount. And it's very benign. You can see how much it impacted my system. Just a few dB I lost. Nothing like those tall spikes that I was showing you when the spectrum was a sine wave or square wave. So random noise tends to be more benign. And sometimes the noise is not broadband like this, and you'll see it here where the bottom of this, I call it the skirt, widens. I call that random low frequency noise. That means it's random, but it's not quickly changing, it's slowly randomizing the clock. Now, question is, how audible are these things? A lot of people are very scared of jitter. They think it can be quite audible. There hasn't been that many studies into audibility of jitter, believe it or not. And the main paper, there are 2 papers. One that tested random jitter, which I just showed you. It's not an issue, and therefore you don't want to go chasing random jitter. And because it just raises the noise floor a little bit and is very benign. So that's a bad study. So if you run into that one, which if you Google, you'll see the paper. You'll see it. The second one, you probably can't find it. It's on AES and was done by Eric Benjamin and Benjamin Gannon when they were at Dolby Laboratories. And they examined jitter. This is a pretty readable paper, much better than Julian Dunn's. And they go through what kind of jitters exists in typical equipment. They measure it. Paper is 30 years old, so the equipment they tested, measured are very, very old. But then they did a cool thing, which is they perform a listening test. And let me scroll down. It's just a few pages down. So you can see, what's the threshold, or what's the lowest amount that we can detect. And they came up with an interesting test in that they had a way to use a function generator and take a clock and literally change the clock of a DAC and be able to change the either drive it with sine waves or whatever frequency they wanted. They went through a good training session and booted out the people that were just too deaf to hear artifacts. And that's a good thing to do. Many of these studies, they take everybody and glom on their results, and you get the people who don't have good acuity for small impairments, and they wind up diluting the results. So let me scroll down to what was going on. So they first tested what would happen if you just had a sine wave, pure sine wave playing, and then you had another sine wave that was jitter, and which then try to add jitter to that. So in this case, they have a 4 kilohertz signal, and they're looking at the jitter amount that was the threshold. Now, this is not a blind test. The listener literally had a knob where they could turn the jitter up and down, and where they thought they could hear it, they said, I heard it, and that number was registered. So it's not a statistical double-blind test where we could tell if these results are 100% valid, but directionally, they're probably okay. We see that with 4 kilohertz, the threshold are very high. We're talking 100 nanoseconds over here for many of these listeners. But as the frequency went up, we see there was one listener here that his threshold was down to 4 nanoseconds, or what I just simulated was 4 nanoseconds jitter. So he was able to hear it. There's some error bars in here, so it was as low as 2 or 3 nanoseconds and 5 or 6 nanoseconds. And then there were some people that were, couldn't hear it as well. So these are the listener numbers, 9 listeners. But you can see that it is frequency dependent in this thing. And then 20 kilohertz, they ran the test. And then they've switched from running sine waves as a test signal to running music. And they had different tracks that they played from these different music. This, again, 30-year-old music. I don't know how many of you remember this Blockbusters synthesized music. It was one of those reference CDs when CD format came out. And now you can see that the jitter nanosecond, the thresholds are insanely high. We're talking 60, even this listener 2, he's now up to 90, 60, 120, 330 nanoseconds. So music tends to mask a lot of these artifacts, especially if the person is not a critical trained listener. It's just going to be hard to hear artifacts. So oftentimes you see people say, well, all these tests are with sine waves. With music, you can really hear artifacts. No. Simple signals bring out artifacts a lot easier than complex signals, because complex signals, there's a lot of spectrum in there that masks the audibility of distortions in there. So, that is not a good argument at all. Whenever we use, in a lot of psychoacoustic research, music is much less critical content as far as threshold of detection for artifacts than simple sine waves. Okay, sorry about the denseness of this topic. I just wanted to make sure that you knew the true fundamentals of it. So just summarizing, don't use your intuition. It is a timing jitter, but it's not blaring things in time, it's not screwing up transients. The moment you read that in the marketing material for anything, just skip past that, because that person doesn't know what the hell they're talking about. Yet 90% of audio tweaks for digital audio, for cables or stuff to put under it, or fancier DAC, they talk about how transients get better. No, it has nothing to do with timing. It has to do with the spectrum of music that can get corrupted. I've measured 400 DACs. I can't, maybe 1 or 2 of them had objectionable jitter so far as audibility. So it is, it's a solved problem, but it's still, as you saw with this device, there are people still not doing the right things. That bothers me. So I measure it and I show it. We show it with this J-test signal that is supposed to aggravate the situation, but it doesn't literally cause any jitter. It's just a signal like any other digital data, and just happens to be specially made with a square wave that's rather clean. And that we like to see a clean spectrum. I don't want to see a whole bunch of unwanted noise from the rest of the processor in this thing, or USB input, or a DSP in case of an AVR, what have you, bleeding into the DAC. It's a revealing test from that point of view. Okay, so hopefully you learned a new topic, and if you did, bet you know more than 99% of the audiophiles who haven't watched this video. Okay, we'll do some lighter weight videos after this one. See you in a future one. Bye-bye.